Well, thanks for everyone to turn up. The presentation we're going to give today is some work that ourselves, Imperas, my name is Lee, are undertaking together with Breker. So let me go through some of the background to this. And in fact, this was the abstract that was put together as part of this presentation. And I think the important thing regarding RISC-V is that RISC-V gives great power to designers to be able to use the ISAs that are presented to you as part of the RISC-V organization, but the capability to extend that as well. I'm sure we're all familiar with this. But the thing is that with great power comes great responsibility. That's one of my favorite quotes from the Marvel films. And we've kind of seen it as being incumbent upon ourselves with respect to the responsibility on the verification side. I myself have been working on verification of RISC-V designs for probably 3 or 4 years now, and I've worked on about 5 different RISC-V implementations. So the talk we're going to do today is to cover some of these aspects of latest developments that we're involved in, that Breker are involved in, and the work that we're doing together. So first of all, let's take a look at some of the challenges. Now, as we know, there is already a process in place for SoC design, and this is what we see, whereby an initial design is done in C, C++ modeling, and then there is a bottom-up bring approach whereby you have simulations of blocks, you tie the blocks together in a subsystem, and then a full system simulation, and ending up in final device silicon. And in terms of the process of core verification, which is what I've been involved in more than anything over the last few years, then we have to ensure that we get good quality verification. And that good quality verification, in effect, means 100% coverage and commercial grade verification. And this is very important for us. Now, coverage of the RTL itself is only part of the story. So you can define a set of coverage metrics as part of your RTL. But in concert with that, what you really need is the ability to have a reference model that sits by the side of this and ensures that even though you're meeting the coverage goals of your RTL, that you're still adhering to the ISA compliance and also any custom instructions that you add into your own design. And more importantly, those custom instructions don't impact on the compliance with the other parts of the specification. And in addition to this, then for the SoC verification and validation, you have to ensure that the processor to SoC functions are correct as well. So now what I want to do is go through a little bit of background of the company I work for in terms of where we started our processes and our products. Our background was actually in trying to develop technologies which allow you to develop software for a virtual platform. Sorry, that's gone forward. And those platforms were built using a JIT compiler, which we built ourselves, with a set of models which allow you to execute code intended for whatever the target environment is on your virtual platform. And we've spent a lot of time providing these types of technologies for developers of the software that runs on the platform. And it just so happens that this same technology was very useful in the design verification flow. And we've recently been working on a technology which we call Imperas DV. And what Imperas DV does is it allows you to provide a configured core that matches the ISA specifications laid out by the organization. But in addition to that, to be able to extend that with your own custom instructions, custom CSRs. And the implementations that you have can be in order, out of order, multi-heart, single heart. You can just about configure this environment to be anything that is valid within the ISA specifications. And by doing this, you can embed this within your environment, whether it be System Verilog or C, C++ environment, and use it in order to ensure that the execution of your RTL matches the laid out specifications inside of the RISC-V ISA specs. We position ourselves as the simulation leader. That might sound a bit arrogant to say that, but we've actually been involved in some of the most complex designs that you could imagine. I mean, even from the very simplest designs of two-stage in-order processors through to multiple heart out of order with vector engines of 2 kilobit vector lengths. We've had some incredibly diverse and complex designs that we've run through the processes that we do in terms of design verification. So we feel that what we're bringing with our technology is, an excellent simulation and verification capability for RISC-V cores. And what we want to do is, in our work with Breker, to bring these two technologies together and hopefully move them forward. So what I'm going to do now is I'm going to pass over to John, who's going to give you some background on Breker and also the collaborative work that we're doing.
Okay. Can you guys hear me? Okay, I think we're good. So, hello everybody, my name is John, and I will talk to you in the next 10 minutes about Breker, about the collaboration with Imperas, and about what we have achieved and what's possible for the future of verification of RISC-V cores. So Breker has been around for a number of years. What we're known for in the industry is the checking of x86 and ARM-based SoCs. We target more of the integrators, the companies that will take the cores, the ARM cores or the x86 cores, and stitch them together to make up a new product. So the way that we have been doing this is through what we call a test suite synthesis. And even though this diagram may seem complicated right now, the basic idea is that you start from the top where you actually present, you are presented with a number of test libraries, things that you can do with your test, that you can apply them in different environments. Our tool simply takes the test library and produces the appropriate test, depending if you want to run in simulation, in RTL simulation, or if you want to run it in emulation, or if you want to run it in post-silicon. Now, this is some of the libraries that we have over the years when we're working with the various customers. One of the things that we have realized is RISC-V has a lot of potential for the industry. And in order for Breker to also produce tests that will apply on RISC-V cores, what we've come up with is 2 new apps in our verification library. We call these fast apps. It is the core integrity and the SoC integrity. What is the core integrity fast app for RISC-V? It is tests that are actually coming straight out of the specification for a single core. You can think of them as compliance tests. This is what we have created all the way to the right. Those are all the different instructions that we have tested and the different tests that we have created for them. So this would be a very easy plug-and-play test solution. On top of the core integrity, as we talk about, we also do SoC integrity apps. SoC integrity apps involve more of a multi-core, multi-heart designs. And if I will have time at the end, I can talk a little bit more about the diagrams that I'm showing here. But let me go through an example of what it means to actually get a Trek app, a fast app, and what it involves. So as you can see, you can have a platform config, which will tell you exactly all the different transaction sizes that can play. Right next to it, you see, for example, the memory allocation. How do you allocate memory in the system? Next to it, it's all the different algorithms that you might want to run. Okay, so this is things that you can specify directly, or you can simply randomize. And then at the very end, we'll add the specific processor instructions. For RISC-V, you can tell us exactly what extension you want to be running. So this gives you an idea of how, not just configurable, but also extendable, the tests are that we provide through these fast apps. So let's talk a little bit about the collaboration between Breker and Imperas. So we see this picture from Lee, and we actually have 2 separate points where Breker and Imperas can collaborate and provide additional value. The first one is where you don't have RTL in the loop. This is very early in the design process. You can take the tests and then compile them into or synthesize them into, and then run them on the Imperas virtual platform. This is one of the collaboration phases, and this is some experiments that we've done there. The other place where we can actually provide value from the collaboration is towards the end of the design cycle. Now, this is what you can run with RTL, with design in the loop, the actual design of the RISC-V core. You will still use the same exact test, and you will now use the Imperas processor model as your reference model. It's going to do the checking for you. So on the left-hand side, by the collaboration, we're going to run a virtual platform. On the right-hand side, what we're going to run is a digital simulation with Imperas model as the reference checker. I think this captures the, like it summarizes the core integrity. We run the core integrity on the Imperas virtual platform. This is the type of things that you can verify. The SoC integrity, we're going to use the Imperas DV technology as the reference model, as I said, and now you can verify more intricate RISC-V designs, designs that have multi-core, designs that might actually talk to different components, designs that have cache. This is one of the collaborations and what we've done where we actually taken a test from the fast apps and we compile it down to a RISC-V compiler, and we actually produced it, played it in the Imperas visual prototyping. Now, the Imperas platform, the virtual platform, has error injection capabilities. And when I talk error injection, I'm talking about not just interrupts or not just the interrupts, but also ability to inject errors into the simulation environment and therefore get the wrong results. And this has been very helpful in order to make sure that our tests go after what we think they go after. It's a way to actually produce quality for the test. Now, the Breker TrekDebug, the GUI, will give you an idea of the scenario and how this scenario displays on the different threads that your RISC-V is running. And you can use it with one CPU, you can use it with multiple CPUs. What you actually have the capability of doing is taking a scenario and then see how that scenario is executed and where the context switches are, where you switch between different processors, between different cores from the beginning to end. And we think this is a very powerful tool, especially when you're getting errors, because you can see not just where the error happened, but you can also see what else was going on in the other cores and the other threads when the error occurred. Another feature that we have is the execution profiling, where if you look at the previous picture, you see that all the tasks, they're equal size. With the execution profiler, we can have it based on the instruction count, for example, and you can see exactly which task took the longer number of instructions to complete. This can tell you if you have a bottleneck in your design. This can give you an idea of if there's any task that you expect them to complete faster than others. So it can give you a lot of feedback of how your design is executing, not just if your test is passing, but also where time is spent or where instructions are spent. So to summarize, just like Lee said, with the freedom comes responsibility. And we're talking about responsibility in terms of millions, hundreds of millions, perhaps, of dollars spent in verification by the big companies like ARM or Intel. So the way for us to actually play catch up and not having to spend $100 million every year to do verification of RISC-V cores, it's the automation that we talked about, the test automation. It is collaboration with the different players in our markets. And it's also not giving the right people the right tools to work with. And that's why we have it broken down into developers. All right, those are the companies and teams that develop the cores, and integrators, which is the teams that take the cores and integrate them to make it into a bigger system or a bigger product. This is our information right there. Lee and I will also be available afterwards. So if you have any questions that we're not going to answer here, come and find us. If you buy us a beer, we'll answer your question. So this is the end of the presentation. Thank you very much. And let's open the floor for questions, comments, ideas. Yeah, I think we have a question. Let's go back up there.
I have to run to you.
Thank you. So my question is about verification of multi-cores. So does your model, so I think this question is for both of you. So does your model have a capability of running multi-cores? And how do we verify using your reference model and your stimulus and checking infrastructure about the cache coherency, and if we have to write any software coherency scenarios around?
Can I first ask for some clarification on that? Do you really mean multi-core or do you mean multi-heart?
Either of them, yeah. But not necessarily multi-threaded in the same core, but if it's multi-heart, it's in different cores. So the question is around verification of the memory system when we have multiple levels of caches, where there could be a L1 cache in each CPU and a shared L2 cache. And then we need cache maintenance operations. How do we verify that thing? Can your model and your checking infrastructure help us with that?
Yeah, so in terms of verification, so I can talk about the test generation and the stimulus, and how about producing stimulus that would actually exercise all the different scenarios that can be possible with a cache. So for example, we would take your cache protocol, and this will be one of the inputs to the tool that's going to generate the test. And we can also take other conditions or other tables that will help us produce the case scenario that will exercise all the different transitions that the state machine within your cache policy will go through. So this is how we generate all the tests. Now, at the end of the day, if we have the Imperas DB integrated into the simulation, I'm pretty sure that by checking not just the memory contents, but by checking values at the end, when you're reading the value, that it's going to tell you if you read back the correct value or not. This is on a read till you actually get the data that you're expecting. And this is exactly what I think Imperas DB is providing, the ability to check the data.
Yeah, that's correct, yeah. So you'd be able to compare the results of the load stores that happen from the processor's perspective.
Good question. Mm-hmm. Other questions, comments?
John, this is for you. I think it was on the last slide you had on the core integrity testing. You showed that the last step was the custom instruction verification. Is that limited to just the predefined RISC-V ISA extensions, or can that handle any user-defined instructions also?
So this will handle the user extended instructions, the customized instruction that you might be putting in. But ahead of time, we don't know what those instructions are going to be. So we'll have to work with you to let us know exactly what to expect and what to add there as part of the instruction set.
Okay, thank you.
Yeah.
Mine's probably pretty detailed. So in this kind of example, you have multiple CPUs going all at the same time. In a real system, if you run it twice, you could get two different results because timing differences. You know, something happened, the cache was warmed up, you get a miss, something happens out of order. So how do you know when something is the wrong result? From a software point of view, you probably know, yeah, I didn't get the result that I thought I should get, but that's a software bug. But this is not software verification. This is hardware verification.
So you
how
talk.
do yeah, like that example, I guess, would be one of them, maybe.
So Lee, is that something that?
Well, from the Imperas DV perspective, then because it's a simulation model, it is always reproducible. I guess what you could do is seed it differently, something like that. But as a simulation model, it is always reproducible, which is not necessarily real world. I think that's what you're saying, right?
Mm-hmm. Any more questions? Yeah.
We're done.
Good. All
We're
right.
done. Thank you.
Thank you very much, guys.
Thanks, Lee and John.